Hi all, welcome back. We're going to finish talking about triple integrals by discussing the third type of alternative coordinate system that we can use to do our integrals, and that of course is spherical coordinates. We just covered the Cartesian system, where we have x and y and z, we have x, y, and z. We also discussed the cylindrical system, where we have r, we have theta, and we have z. And that worked for us. Now we've got one final system to discuss, and that is the spherical coordinates. Now again, I'm not going to really go over many examples or any examples with this. I just want to lay the groundwork. What is the measure for the differential volume? What are the conversion formulas? You guys are already pros at converting the equations to the proper variables, and also determining what your bounds of integration are. We spent so much time covering that with double integrals. We should know how to do that by the time we get to triple integrals, so I'm just introducing another way to do things with these spherical coordinates. So let's take a little look at what these spherical coordinates actually are. The hint is in the name, the fact that they are spherical. What we are going to do is we are going to take our x, y, and z plane, and I'm not doing this coordinate system justice because I'm drawing it and I'm not good at drawing. We are going to take a sphere and consider this as some arbitrary point on the sphere. This has components x, y, and z. So we have a z component, we have an x component, and then of course we have a y component here. And what we are going to do is we're going to draw a vector, not really, it's just a line or something, to it. Its magnitude, the magnitude of this vector, we are going to call rho. The magnitude of that vector is rho. We're also going to draw out a radial vector just on the xy plane, right? So we have our x here, our x, our y, and our z, right? What we are going to do is we are going to define this angle, the angle from the z-axis to rho, to the line created by rho. We define that angle as phi. You could call it phi or phi, I call it phi. And then also, similar to how we do it in polar coordinates or cylindrical coordinates, we are going to define the angle between r and the x-axis as being theta. So what we have done is we have gone from something describing x, y, and z, a point x, y, and z, and we have gone to a rho theta phi. So rho theta and phi are completely angular, or they're either radial or they're angular. There's no Cartesian linear coordinate, right? We have a radial vector, or we have a radial coordinate that determines how far away from the origin it is. And then we have two directional components, which are, of course, the xy angle variation theta and the yz variation of phi. And it's very important to remember the importance of where you put these angles. This needs to start here and end here. This needs to start here and end here, else you might have trouble with your integration bounds. Anyways, let's do some of the conversion formulas. And also note that this, once you draw it out, this if you keep it at constant, rho theta and phi will sweep out a sphere, and rho will will allow you to create whatever size sphere that you want. Anyways, we define z as being rho times the cosine of phi. That should make sense. If I have this triangle here, if I have a triangle here with rho on one side and phi on the other side, and then that's going to be my z. Z is equal to rho cosine of phi. We define r as being rho sine of phi. So r is going to be this quantity here, and this is defined as rho times the sine of phi, okay? And then we also have the equation that says rho squared equals x squared plus y squared plus z squared, and that should obviously be fairly simple to remember. Anyways, now we can look at our formulas for converting between x, y, and z and r theta phi. If I have an x coordinate, I can find, if I have a function defined in x, y, and z, I can convert it to spherical coordinates by using rho sine phi cosine theta. That, again, should make sense if this is my x coordinate, using our theta and our phi and our rho to determine what that is makes sense. Y is going to be rho sine phi sine theta, and Z is going to be rho cosine of phi. That says theta, but it should say phi, right? Okay. Anyways, if I have a differential volume, so if I have my sphere and I have some sort of differential volume, well, what are its dimensions going to be, and what do I need to tack on at the end of an integral? Well, if I want to take the integral of a three-dimensional spherical unit, then I will need to convert that into the integral of rho squared sine phi d rho d theta d phi, right? So this is our measure. Similar to how in cylindrical coordinates we had dv equals to r dr d theta dz, we have a new formula for spherical coordinates that is a little bit more complicated, but it works out. And I'm not going to derive this, and the reason is, sorry, I was about to sneeze. The reason is that in the next video, we're about to learn something called the Jacobian matrix, and the Jacobian matrix generalizes this so that we can convert whatever we want, whatever sort of coordinate system we want, into a differential, into some sort of differential. So if I want to change variables to something else, I can do that, and we'll use the Jacobian matrix to derive this and to derive